we're going to look into tracking information flow across programs, which is a very valuable technique as it comes to fuzzing, but even more so in the context of security testing. What does it mean to track information flow? I'm going to give you a simple example of how that works. Let me share my screen here and let me see whether things work. So, the problem we are tackling today in this context of security testing is a fairly simple one. So suppose we're having some SQL command which fetches a row from a table. Something like select star from customers. Let's make that customers. Why not? Customers where... Is that actually the way to do it? Well, let's make it this way. From customers where user equals... Hi, Marius. Marius. Here we go. So this is a simple SQL command which you can use to fetch things from a database. Select star from customers where user equals Marius, and if you actually execute that, you're going to get all the information about Marius that is stored with us. That is his first name, his last name, where he lives, his credit card numbers, his recent purchases at Amazon, and his pending purchases at Amazon, and how to actually have all these things sent your way and paid by him. Well, that's a customer's database. Okay, but we're actually not doing this, Marius, so you can be happy. No worries about that. Okay. Now, of course, the whole thing would typically be parameterized. So what we typically have is we're having some variable named username, which is called Marius. Okay, great, wonderful. Here we go. And now our SQL command actually does not look like this, but in fact it looks something like this. So it's actually parameterized. So we're having username in here plus the finishing opening quote. There we go. Wonderful. And you can actually find out that the final SQL command still is the very exact thing as here before. So all of this is very fine, and you're going to find these things in hundreds and hundreds of individual implementations. Now there's a slight problem with that, with this kind of code, because typically it is users who specify their username, for instance, for logging in. Okay? And if you now have a username that says, we're going to make things a bit hard here. If you have a username that actually says, quote, semicolon, drop table customers. There we go. Isn't that great? Yes. And finally a comment, because we can. Okay, this is a SQL comment. Okay, great. As just this thing before. This is what you see here. Okay, now I've entered a new username. Let's assume that this is my username. And now we again compute the SQL command in here using the same code as we had before. Oops, sorry. So we're taking this piece of code and we put it down here. Here we go. Wonderful. And what does our SQL command now look like? Well, your SQL command now has the interesting feature of still selecting things from the customer's database. So far so good. Now the user string is empty, so it's not going to select anything. But the interesting thing is that right after selecting all these individual items, it's going to execute another SQL command, namely drop table customers. Drop table customers is a command that's going to delete the entire table of customers. Actually, you cannot execute this command twice, because the second time it's going to tell you that the customers table just has disappeared. And instead of drop table customers, you can do other things. You can, for instance, give a command, insert into customers whatever data you want, or update table customers where user is Marius to set the password to 0, to set an arbiter to say that I have I actually do have a big Amazon gift card where I can now buy a new Tesla from or whatever. So you can do arbitrary can do arbitrary manipulations of the database, and that's of course something you don't want. This whole thing is known as a SQL injection attack. And yes, this here, if you ever wondered why your name in databases as well as on your passport cannot contain certain characters, I think single quotes are fine, but semicolons are actually not. This is the whole reason why this is not allowed. By the way, if your name is D'Hondt, for instance, a famous mathematician and statistician, you already run into trouble with plenty of systems, because the quote in here will actually be interpreted as quote in many systems. When my wife and I decided on names for our kids, we explicitly chose names that would work well in 7-bit ASCII in order to avoid any current and future misinterpretations within systems. Well, the 8-bit ASCII thing has somewhat gone away. Now it's more of a Unicode problem. But definitely do not put apostrophes in your name unless you want to break something. Okay, now I am actually digressing here. How can we prevent this kind of thing from happening? And this is where information flow comes into play. We're having an interesting class here, two classes that are called tstr and ostr, or more precisely tstring and ostring. Both of these are extensions of the Python string class that allow you to track additional information. I can put something into an original or into an ostring, and for instance, the username, as we just had it before, let's make that Marius one more time. And then nothing is going to happen. My username still is just as before. I can use it as a string. I can use it into all sorts of contexts as well. Marius Miller, for instance. Let's make that go ahead. Marius Miller is around. Here we go. So I can use it as a string for all kinds of purposes. However, the interesting thing with our extra classes is that I can attach a so-called taint to them, which is a label that automatically is attached here. So we can actually tag the whole thing. We can tag third-party input with the label insecure. And now the username still has the same properties as before, but I can access the taint in an extra attribute, which is called taint. And I then know that this input has come from a user, from a possibly non-trusted party, and therefore is insecure. And now the interesting thing is that this taint actually propagates across various parts. So if I have username plus, plus a regular string, make that Miller, here we go. And I can access the taint, then the whole thing is still insecure. And if I have a SQL command like this one, select star from customer with user and so on, blah, here we go. Then we can access the taint of this SQL command and hopefully, yes, it works. I'm so happy. And still find out that this SQL command is insecure because it contains strings that have been under control of a third party. Therefore, whenever we compute a SQL command and we execute it, we should make sure that its taint is not insecure. How do we do this? Well, we define what we typically do is here we define a Sanitize function that takes some user input and then goes along and happily remove or quote all insecure characters. That is something like I don't have the command for actually replacing things right now in my code, but what I can do here is now I can identify all elements in my string that are not letters or letters. I think it's just letters. Well, spaces. Spaces would probably also be allowed, and single quotes. And I would go, and anything that is not part of a regular username should now be removed or sanitized. Sanitized means that we can put an escape character in front of it such that it will not be interpreted as a SQL command. And then I can go and compute some. Let's assume that this is in sanitized, and then I can say, okay, now the taint of sanitized is secure, or secure, something like that. And then I can go and return the sanitized string. There we go. So, and if I have that, then I would go and compute my SQL command from not only the username, but the sanitized username. Here we go. And if I do that, oops, I did something wrong. Sanitized is not defined. Oh, how could I do that? Sanitized is an O string. Here we go, blah, 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 whatever. Marius, make that simple. Okay, here we go. And we execute the whole thing. Sanitized is not defined. What do I do wrong? Sanitized. Here we go. Sanitized is not defined. Come on. Sanitized of user input. Here we go. Finally, we have it sanitized. And now I can actually go and check out the current SQL command taint. And we're going to find that now it is secure because all the characters that come from user input have been properly sanitized. Okay, that's fun. And in the chapter, you're going to see how to use such information flow, not only to find out not only to attach individual labels to strings, but also to attach origin information to some strings so we can track where a particular character actually came from. We can also use this to track it where it came from in a big input, and then use this, among others, to decompose a big input into smaller parts and bring things back to their origin. The interesting question is, however, how does this work? How can I go and simply attach some extra information to a piece of to a variable that actually also gets propagated across complex expressions? Well, there's two answers to that. A, you do this in Perl, the programming language Perl, P-E-R-L, where this is built in, period. Option number two, and then you have it. Option number two is you do this in Java or C or Fortran or any language of your choice, and you're going to spend a couple of months building it. Option number three, of course, this is our option, is to do this in Python. And in Python, it's actually fairly simple to do that. Fairly simple meaning relatively simple. Let us take a look into the chapter on information flow, where these two classes, tstring and ostring, are actually implemented. So here we have an introduction to tstring and so on and so on. You have a couple of examples with our database and everything. And now the way this works is actually extremely simple, because here we have the original string objects in Python. We can create a subclass of this string class, just as we do subclassing of other classes just as well. So we can create a new class, tstring, that is a subclass of string and therefore compatible with anything that a string provides, which is neat. And now we have our constructor here. There we have a constructor here, which takes a value, which can be anything. well, typically a string, and where we can add an extra taint, which is also anything in here. And this taint, self.taint, is assigned this taint over here. Just don't care about the extra type information here. Self.taint is of type any, values of type any, taint is of type any. Actually, you can put in anything here. Okay? And the only thing that you need to know here is that if you wanted to define your own string class, there's also a second method that you have to override, which is the new method, which creates a instance of the given class. If you do not do this, then the string that you create will still be will still be the original string and not the t-star string. This is one of the dark corners of Python. If you search on the internet for how to subclass the string class, you're going to find these hints on how to do that. I can tell you not many people are doing that, but you can do that, which makes things very easy. Okay, so now we can initialize one of these strings and we can give it a taint, and the taint automatically becomes an attribute in our class. And now the rest that we have to do is homework. We have to make sure that we can convert, that we have a representation of our string. And this representation of our string, for this we simply go into the representation method of the original string class, except that we also add a taint to it and make the whole thing a tainted string. So whenever we can, we try to keep the taint and propagate it further. The exception being when we need a regular string, not one of our strings, but just a regular string. That's when we simply convert the whole thing into a string. And then after that, what we have to do, and this is somewhat painful, is for all the methods that strings support, capitalize, casefold, center, encode, replace, a swap case, whatever, title, okay? All these methods need to be set up such that they also propagate the taint towards the new string that is being made. And for this, we have an extra helper function, which is called makeStringWrapper. And this makeStringWrapper actually goes and creates a method that propagates the taint as we have it in here. That's a bit of magic, but it's not too complex because all we have to do is to propagate this very taint. And once we have that, then we can use this for all sorts of things. So we can access individual elements of a string, and we can also access slices of a string, or we can put things together, or we can we can also, if we have a tainted string and add more strings to it, regular strings, the taint will remain the same. There's also multiplication. If you didn't know, in Python you can do multiplication on strings. If you multiply a string 5 times, you get the concatenation of these strings 5 times after the other. Yes, and the taint remains in here all the time. And with this is how we can then implement information flow and do some actual security checking here. In the chapter, you're also going to find how to use this information for targeted fuzzing, notably for also tracking the origin of individual characters, and using this information to actually do advanced grammar fuzzing in order to figure out how to specifically target a particular element, a particular string in the program. Because if you find that in some condition you have a string, and this string is a part of the original input, and you want to change that string, then by using information flow tracking, you can track the origin of the string. You can find out via the taint where it came from, and then you can just go, okay, I know that the string came from up here, so I'm simply going to change things up here. This is what we're having about information flow, and while information flow can serve as a means to fuzz in itself. It also creates a great helper for the technique that we're going to introduce next, which is called concolic fuzzing.